All right, hello everyone. Welcome to our newest edition of the Long Range Colloquium hosted by the Virtual Science Forum. I have a brief advertisement before we begin, which is a new initiative that we've launched called the Speaker's Corner, which is a seminar series in which you can invite yourself to give talks at exactly the time it's most useful to do so, which is exactly the moment that you have something to say. All we ask is that you bring your archive posting with you, and you can already go to our website at the link below to submit a proposal to give such a talk, and more details are located at the link. You can contact us with any more detail. Let's ask for any details you need. Today, we're excited to have Brian Skinner from Ohio State University just this year. Personally, I have always admired Brian's approach to finding interesting things where most other people aren't looking, which has ranged from dynamical and statistical phenomena in human behavior in sports, all the way to localization phenomena in quantum materials, which have provided a lot of deep insights into our understanding of the realities of materials that we actually work with in the lab. And today he'll tell us about yet another interesting venture of his. Brian, please take it away.
Okay, all right, thank you very much. I am now minimizing all the Zoom windows that I can see my own screen. So if there are questions or something like that, I'm mostly not going to see it, and I'm going to rely on someone to yell out and stop me. So I apologize for that in advance.
Yes, please raise your hand, and then I or one of the other co-hosts will alert Brian to your question.
Okay, thank you. All right, well, thank you very much. Thank you for this opportunity to give this talk. Like a lot of us, I guess, when the pandemic started, I sort of got nervous that we were all going to end up sort of isolated from each other and unaware of the good work that we were doing. And it's been really nice to see seminar series like this and other ones. And I think, if anything, my access to really high quality talks has improved since the pandemic. And it's very exciting to be part of this seminar series, and I hope that I can live up at least a little bit to the very high standard that previous speakers have set. Okay, so this is work that I did with these three people. There's Adam Nahum and Stithiti Roy, who are both at Oxford, and Jonathan Roofman, who's at Bar Ilan. And I should probably say from the very beginning that I am in no way like a senior member or a leader of this collaboration. Any of these three people could give a talk that's at least as authoritative and at least knowledgeable about this subject as the one I'm giving. It just happens that I'm the one doing the talking today. The other apology I should make is that I'm sort of going to try to overview these two papers. Oh, here, let me turn this into a... I'm going to try to overview these two papers, one that came out in PRX last year and one that we just put on the archive a couple of weeks ago. These are both pretty long papers. It turns out that combined they're about 90 pages long. So this talk is necessarily going to get a little schematic along the way, but I hope that you can at least get the main idea of what we did and why it's interesting. Okay, so this talk is about quantum entanglement, and maybe before I describe the specific problem that we're interested in, I should give you an overview of how we think about quantum entanglement and how we quantify the degree of quantum entanglement. So the usual definition that we make of quantum entanglement is that a system is quantum entangled when the state of the system, in terms of the wave function, cannot be specified by describing all of its components independently. So let me just contrast two well-known situations. Imagine if I had two quantum objects, let's say they're spins, A and B. In an unentangled state, it's possible to write the entire state of the system as a product of the state of A times the state of B. This is a product state. And in that sense, both A and B are specified independently of each other. Whereas in an entangled system, or an entangled state, it's not possible to write it as two independent pieces multiplying each other. So this is for example, the well-worn singlet state, where your wave function looks like a quantum superposition of A being up and B being down, or B being up and A being down. And in this state, the wave function is not decomposable into something that only relates to A and multiplied by something that only describes B. Now, this is the usual description, but the perspective I'm going to take in this talk is mostly a slightly different but equivalent one, which is that I'm going to say that a system or two objects are quantum entangled anytime that making measurements on B alters the state of A and reduces the set of possible measurement outcomes. So in particular, let me just start with this product state. Now before, let's say A and B are in some generic state that's neither exactly up nor exactly down. Now if I make measurements on A, I can either get up or down probabilistically. make measurements on B, I can either get up or down. But importantly, if I measure B, then I'll collapse the wave function into something where B is definitely up. But any future measurements on A will have the same range of outcomes as they would have had before making the measurement on B. Now compare this to the situation in a singlet state, which we would say is entangled. Now if I make a measurement on B, and let's say I happen to measure that B is up, then any future measurements on A will definitely yield down. So I have reduced the set of possible measurement outcomes for A by virtue of making a measurement on B. Now what I like about this perspective is that it immediately suggests a way to quantify how entangled two things are. Because you can talk about by how much have I reduced the set of possible measurement outcomes on A by virtue of making measurements on B. How much, or equivalently, how much information about A is stored non-locally in B. So the first point that I should make is that whenever you talk about entanglement, you always have to say entanglement between what and what. You always have to define two subsystems, so A and B. So for most of this talk, or at least the first part, I'm always going to talk about the entanglement between, say, the left half of the system and the right half. And now I ask, how much information about the left half is stored in the right half, or how much can I alter the state of the left by making measurements on the right? So one way to do that is to start by writing down the density matrix, which is this outer product of the wave function with itself. Now at this point, I should make the point that everywhere in this talk, I'm going to be talking about pure states, which I mean systems that are described by a specific wave function, as opposed to what you call a mixed state, which is a statistical superposition of different wave functions. Okay, so once you write down this density matrix, if you want to get at the question of how much do measurements on B change the state of A, what you could look at is the reduced density matrix, which is basically you trace out B, or you sum over possible measurement outcomes of B, and you get something that looks like a new density matrix, the reduced density matrix for A. What you can think of is that a system described by a wave function is a pure state. It has no entropy to speak of. It's in a definite state. But if I sum over the possible outcomes of B, then measurement outcomes on B, then what I'll get is something that looks like a statistical superpositions of different states that A can have, given different possible measurement outcomes for measurements on B. So this reduced density matrix no longer describes a pure state. It'll look generically like something that's mixed, and how mixed it looks depends on how entangled it was with B. So now if I want to quantify how entangled A was with B, what I can do is calculate the entropy of the reduced density matrix. So it looks like trace of rho log rho, and this should look somewhat familiar to the normal way we talk about entropy in statistical physics as the sum of P log P. So the entropy of the resulting distribution. So I'm calculating how much uncertainty is there in A, given the possible measurement outcomes that I could have when measuring over B. And I'm going to refer to this object as the entanglement entropy of A with its environment. Okay, so the general question that this talk is interested in, and that's become a big topic of interest recently, is how does entanglement evolve in time? So we have, in physics, we have lots of different types of dynamical problems. We have, problems about diffusion and random surface growth, etc. But what kind of dynamics describes how how entanglement evolves in time? So a major tool for addressing these kind of questions, or modeling this kind of question, is what you'd call the unitary quantum circuit. So the idea is that you have some set of spins or qubits, and you describe the evolution in time via a series of discrete unitary operations. So what you should see in this picture is time progressing vertically upward, and each one of these blocks corresponds to a unitary operator that's applied on two spins. So you apply some unitary operation that now changes the state of these, that acts on the Hilbert space of these two spins and changes the state. So a picture like this could describe something like a sequence of quantum gates, like operations you perform on a quantum computer. You can also use unitary circuits to describe continuous time dynamics, like you might have for a Hamiltonian. Basically what you do is you break a continuous time evolution into discrete little blocks like this, and it becomes a way of approximating a continuous time dynamics. So what I want to talk about in this talk is random dynamics. And by random, I mean that there will be randomness in some portion of the unitary evolution. So for example, randomness in the way the way that these unitary operators are applied in time, or randomness in the operators themselves, that the operators themselves are somehow random. Now, this kind of problem about how entanglement grows with time has been the subject of a lot of recent work, and surprisingly, it's only been a few years that we've seen just a huge amount of progress on how to describe this type of problem. This list of papers here on the right is in no sense comprehensive or anything. It's just some of the papers that have been more prominent in my reading of the literature. And what people have done is try to map this problem of the growth of quantum entanglement onto some kind of effective statistical mechanics problem. And there's been a lot of clever and creative work in that direction. For the purpose of this talk, I only want you to know maybe the most basic detail, which is that entanglement tends to grow linearly in time. So if I have a system that's described by some kind of random unitary dynamics, I partition it into the left half and right half, and I ask how much entanglement is there between the left and the right, given that you start in some unentangled state, like a product state. And the answer is that it tends to grow linearly in time with some rate that I'll call the entanglement velocity, VE. And if you want a really schematic way to think about what's happening here, what you can think is that if you start with a system that has no entanglement, after you evolve the system for a little bit, you'll start to have entanglement between, say, a given spin and its neighbors. So one way you can say it is that the information that was originally encoded locally in a particular spin, so either an up or down, now starts to get scrambled over a region containing its nearest neighbors. And as the evolution continues over time, that information is scrambled over an increasingly wide region in space. And as the temporal dynamics continues, that region grows wider and wider. So more information that was originally encoded on A now leaks into B. And that sort of linearly growing length scale leads to a linear growth in the entanglement. Now, if you wait a sufficiently long time, eventually you'll get to the situation where all the initial information in the system is completely scrambled over the entire system. And then you have an entanglement that is, say, between left and right, that is proportional to the system volume. So that's what you call volume law, proportional to the total number of spins in the system. Now, the question that we're interested in is...
Right, I think we have a question from Babak, is that right?
Yeah, please.
Oh,
maybe I may have misinterpreted the clap icon.
Oh no, sorry. I was talking, but I didn't know that. I think we got, I was still muted. Sorry, so the initial growth here, is that, does that depend on the dimension of the system?
Yes.
The functional form?
Right, so the way you can think about it is that if you had, okay, so you're right, I'm talking so far about a one-dimensional system, and I'm going to talk about a one-dimensional system for the first half of the talk. If you had a two-dimensional system, like imagine a square lattice of spins, then you would have this sort of same argument about you have a growing length scale around the boundary between A and B that's leading to the same linear growth in entanglement. So the linear growth does not depend on the system. It does depend on the area of the boundary between your two regions.
Okay. Mm-hmm. Yes.
Okay, sorry, did that answer your question?
Yes. Mm-hmm.
Okay.
Thank you.
All right, so in this talk, I want to talk about not just entanglement growth, but entanglement growth with measurements. So the point I want to make is that the existence of this unitary dynamics tends to make entanglement grow as a function of time. But you can imagine now a system that's sort of sporadically monitored. So someone comes along and measures one of your spins. And whenever one of those measurements happens, it tends to reduce the entanglement, basically by collapsing some degree of freedom, and whatever information that used to be spread out is now localized to a specific point. So the question we became interested in is, what happens to a quantum system that's undergoing both unitary evolution and the sporadic measurement? How do these two factors compete with each other? And this is sort of an interesting and new kind of dynamical process that we're really still in the early stages of understanding. And let me just spoil the punchline here from the very beginning. The result I want to try to explain to you, or that I want to, is that there is a phase transition associated with the measurement rate. That when the measurement rate is low, you continue to have linear growth in the entanglement that ultimately saturates something of order the system size. And when the entanglement, or when the measurement rate gets bigger than a specific critical value, you have a phase transition to a dynamical phase where the entanglement stops growing and saturates to something small and finite. And this is the result that I'm going to try to explain to you in two different contexts. So in the first part of the talk, I'll tell you more about this one-dimensional circuits, or 1 plus 1D, one space dimension, one time dimension. And in the second part, I'll tell you is sort of an infinite dimensional version of the problem where every spin is directly coupled to every other spin. Okay, so let me state specifically the problem in 1 plus 1 dimension. The problem is, the sort of protocol is that you can imagine having a one-dimensional line of spins, and now you apply, in some regular way, unitary operators at each of these bricks. Each unitary operator I'm going to take to be just a random unitary quantum gate. So you select at random in a random way from the set of all possible unitary operators. You apply it between two spins. And in addition, I'm going to have measurement happening at some uniform rate. So every place you see a black dot in this picture is the location of a possible measurement. So at some uniform rate per spin per time, I will make a single spin measurement, just project the value of that spin into some value, which I'll make a measurement of the z component. And so this model has only one parameter, which is the measurement probability p. The probability p that a given one of these dots will be a measurement. And the result that I want to try to explain to you in this context is that when the measurement rate is lower than some critical value, the entanglement may grow a little bit from the beginning, but then it will saturate to a constant that's independent of the system size. And when you have a measurement rate lower than some critical value, the entanglement will continue to grow with time, although the rate of growth can depend on the measurement rate. And then exactly at the critical point, you'll have a logarithmic growth of entanglement with time. Okay, so before I explain to you where this result comes from, I think it makes sense to start by asking the question, under which situations can I be sure that there is zero entanglement between the left and the right? So imagine this sort of hypothetical quantum circuit where these unitary operators are now acting on adjacent spins, and I start from some product state that has no entanglement between left and right. And you can see that in this situation, at the final time up here, I'm going to have the left in some entangled miasma with itself and the right very entangled with itself, but no entanglement between left and right. So you can say, I can imagine now just cutting the system in half, and the two quantum circuits are completely independent of each other. So there's no entanglement. Now consider a slightly different situation where I do have these measurements that now connect, I have these unitary operators that connect the left and the right, but I make measurements of, say, this spin that's adjacent to the midpoint over and over again. Every time step, I keep measuring the value of this spin. Okay, I'll call this spin 4. So if you sort of walk through what's happening here, okay, initial time, nothing's entangled. After time 1, now spins 3 and 4 are entangled with each other, but I immediately measure spin 4. I project it into a definite state. So now spin 4 is not entangled with anything. Now in the next time step, I apply this operator that is going to entangle spin 4 with spin 5. But importantly, spin 5 does not become entangled with anything else to the left because 4 was in a definite state. Okay, but now I'm going to immediately measure 4 again. So now 4 is projected to a definite state. And again, 5 is not entangled with anything to the left. So you can imagine just continuing this process. I measure this spin at the boundary over and over and over again. And by virtue of that measurement, nothing on the right can ever become entangled with anything on the left except briefly spin 4. So I sort of prevent entanglement from forming between the two sides. Now, in terms of drawing partitioning the system, what this means is that I can sort of draw a line that separates a left half from a right half and goes through the location of measurements. And now I can say that anything on the left is sort of causally disconnected from anything on the right, and there can be no entanglement between them. Okay, so you can play with different examples. Here's just one more, I guess, where I evolve the system initially so that everything becomes entangled with everything else. Then at some time, I measure everything on the left, so it comes to a definite product state, it's not entangled with anything else. And then I do this business of measuring the spin right at the midpoint over and over again. And you can sort of see that, again, I can separate this part on the left from what's on the right. You can imagine sort of grabbing the top left corner of the circuit and then pulling it away from the rest of the circuit, as if these measurements represent breaks in the circuit. Now let me briefly make one small modification. Let's just say that I remove this measurement right here. So now I have this situation where I can no longer say that the spins on the left at the final time are completely disconnected from the spins on the right, because there's this one piece of evolution of a single spin that connects them. But what I can say is, look, this is just one spin at a given instant in time. One spin can carry at most one bit of information. And what that means is that the entanglement between the left and the right at the final time cannot be bigger than log 2. The entanglement entropy can't be more than log 2 because I'm only transmitting at most one bit of information that's relevant. So this is one of the key insights of this paper that, in my view, really helped to kickstart a lot of this interest in dynamics of quantum entanglement. And what it means for this problem with measurements is that you can sort of generalize, or you can take as a general rule of thumb, that if you want to know how much entanglement exists between the left side and the right side at the final time, the question you can ask is, if I wanted to separate the circuit into disconnected pieces so that the left at the final time was completely disconnected from the right at the final time, how many links would I have to cut in this circuit? Because each link can transmit at most one bit of information. And so if I only have to cut, say, one link to disconnect them, that means the entanglement can be at most 1 log 2. And if I have to cut some number that I'll call S0, then generically the entanglement will be at most S0 times log 2. That forms an upper bound of the entanglement. Now, phrased in this language, the question of how do I understand, this upper bound on entanglement becomes equivalent to a percolation problem. So this is, in my knowledge, was actually the very first percolation problem, and the reason we refer to it as percolation at all, because you imagine sort of water dripping down through a porous medium, and you ask, if the water wants to flow from the top to the bottom, how many blockages does it have to move through? And in our problem, this problem of percolation, which we call first passage percolation, gives you a bound on what the entanglement entropy can be. Now, I'm going to talk for a while about this S0, which is sort of a classical toy model for the entanglement transition. But I'll just mention that there actually are well-defined limits in which S0 becomes an exact descriptor of the entanglement. Basically, that's the limit where your spins are not spin 1/2, but some spin q, and you take the limit where q goes to infinity. So in other words, where the local Hilbert space dimension of a given qubit goes to infinity. And roughly the idea is that when the local Hilbert space dimension in which your wave function lives becomes extremely large, then a randomly chosen state in that Hilbert space is always very, very close to a maximally entangled one. And that's roughly where this picture is coming from. But anyway, for me, I want you to think about this classical problem as a sort of toy description of the entanglement transition that we can use to build intuition. Okay, so when we first reduced this problem when we first made this mapping between the entanglement transition and percolation, I got really excited because this picture that we had just drew looked very similar to the very first percolation problem that I ever encountered. This was my first college physics class by a guy named Dick Zallen. This is a picture from his textbook. He made a career studying amorphous semiconductors. And the problem that he introduced us to or he introduced me to, was the problem of what he called the vandalized resistor grid, where you imagine a square grid of 1 ohm resistors and formed in a large square shape. And you put a 1 volt battery across the grid and you ask how much current goes through the grid. And okay, when the grid is completely intact, then you get 1 amp of current, you have effective resistance 1. But now you can imagine that some vandal comes along, that's this guy, and starts cutting links at random. So it starts cutting bonds in your resistor grid. And the resistance of the grid starts to rise, the current vanishes, and at some critical fraction of cut links, what you'll find is that a very large grid will fall apart into disconnected pieces. And the left electrode here will become literally disconnected from the right. Resistance goes to infinity and current drops to 0. And you can think of this as this is a critical behavior, which you can think of as akin to a phase transition. So what are the implications for our problem? Well, I've sort of showed you that the question of how much entanglement exists in this circuit is equivalent to the question of how many cuts do I have to make to separate the top left from the top right. So let's talk about that problem. Now, starting with, say, the case where there are no measurements, so none of these links in the circuit are broken. And now, okay, let me imagine that the number of spins is very large. This circuit goes on for a long time in both the left and right directions. And now, if I want to separate the left side from the right side, I have to make a cut that sort of goes vertically downward. And the number of cuts that I'm required to make grows linearly with time. So I'll have an entanglement that grows linearly with t. All right, now let's imagine that I start to make lots of measurements. And this initially intact grid will start to look like a ripped up fishing net, it will have big holes in it. And the size of those holes is given by the correlation length. So the correlation length has some critical divergence as you approach the percolation threshold. Now, what I'm not drawing here is that you will also have lots of little dead ends and small clusters that don't matter for the question of how much I have to cut the net to disconnect it. And instead, I can just think that there's sort of a percolating backbone, which has a characteristic hole size in it, which is this correlation length psi. So now if I ask the question, I want to separate the left side from the right side at the final time, how many cuts do I have to make? And the answer is you have to make 1 cut per correlation length. So here, 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 and here. Correspondingly, if the length of your time evolution is t, then the number of cuts looks like t over psi, where psi is this correlation length. So in other words, your entanglement grows linearly in time with a rate that vanishes as you approach the percolation threshold. So what happens exactly as you approach the percolation threshold? So as you approach the percolation threshold, this correlation length diverges. It eventually becomes infinite, or of the order of the system size. And at that point, your system sort of no longer has any characteristic length scale. And what you should think is that instead it has like a fractal structure or a fractal distribution of all different length scales. And for our problem where you're trying to cut the system into 2 halves, what you can think is that your cut now has to pass through a fractal structure of different empty chambers. So generically, your cut is anchored here. It has to start from here. And generically, it will open up into a void of size 1. But from there, you can pass to a void of size 2, and then to size 4, and then to size 8. And you pass from one length scale to another, and you make 1 cut per length scale. And ultimately, by doing that, you'll be able to separate the circuit into 2 disconnected parts. And so what it means is that the number of cuts, which is our estimate of the entanglement, grows like log of t. Okay, so this is sort of me trying to give you a heuristic feeling for what is a classic result in percolation, that the first passage percolation it goes linearly in the system size, or logarithmically in the system size. All right, finally, if you go beyond the percolation threshold, meaning you cut so many bonds that your system, your network has now fallen apart into disconnected pieces, your minimal cut, which might start generically up here, will have to pass through a few chambers up here until it gets to the scale psi, and then it can freely move around all the way to the bottom, by which I mean you really only have to cut through this initial piece, which might connect, say, the left half to the right half. But once you've done that, you're done, and your cut no longer depends on the system size, which is in this case the time dimension. So the point is that on the non-percolating side, your entanglement grows only as the log of psi, which is a logarithmic dependence on the measurement rate. What you can do is you can put all 3 of these regimes together and say that what you have is that when you're below the critical measurement rate, you have an entanglement that grows linearly in time. At the critical measurement rate, it grows log in time. And above the critical measurement rate, it has no dependence on time anymore. So as in any critical phenomenon, it should be possible to write these 3 regimes in terms of a scaling function that depends only on the ratio of the system size to the correlation length. So the way you do it in this case is you write the entanglement minus the entanglement at the critical point. So that's S of P minus S of PC. And you get a function that depends only on system size relative to the correlation length. So in the limit where your system's, your number of spins is infinite, this becomes something that depends only on t. You can imagine taking the opposite limit where your system size is fixed, your number of spins L is fixed, and you instead look at the limit of t going to infinity, and you'll have a similar scaling function. That's now a function of L over xi. Okay, so here is an exact simulation of this classical problem, this minimal cut problem. And what you're seeing here, sorry, this is a double log scale. So anywhere you see something that looks like a slope 1, that means that the minimal cut is growing linearly in time. And the vertical offset means that the coefficient of the linear growth is shrinking as you go from 0 measurements to lower measurement rate. But you can see that when you go above, for 0 measurements to higher measurement rate as you go down. What you can see is that when the measurement rate goes above a critical value, this minimal cut stops changing with time. It just is a constant that's now independent of the time. Okay, and if you take this curve right in the middle here, which is right at the critical value, maybe that looks like a logarithmic growth in time. I guess it's hard to tell. But if you plot the rate at which the entanglement grows with time, what you see is that it has a critical vanishing at some critical measurement rate. And it turns out that this is exactly the dependence that was in my Professor Dick Allen's book. And you can just read off from that problem, what is the critical point? It turns out to be exactly when exactly one half the bonds are cut. And what is the critical exponent? That's nu equals 4/3, the critical exponent associated with percolation in 2 dimensions. Okay, so you can take these different curves that are different system size as a function of time, and it should be possible to scale them all on top of each other. So here what you're seeing is the value of this minimal cut as a function of the measurement rate P for different system sizes. And what you can see is that over here, when the measurement rate is large, the value you get for this minimal cut is independent of the system size. It's the same for any system size. And when you have a lower than critical measurement rate, now the value depends strongly on the system size. But you can scale these like I mentioned a couple slides ago. You can write all these curves as a function of only a single scaling parameter, which is like L over xi, and all this data scales right on top of itself. And this is no fitting parameters here. This is just using the scaling parameters for 2D percolation. Okay, so this is the sort of the classical toy problem. What does it look like if you simulate the full quantum circuit? Now this is what you're seeing here. This is an exact simulation of the entanglement entropy, which you call the von Neumann entanglement entropy, as a function of the measurement rate for different system sizes. And what you're seeing is that, again, when the measurement rate is large, all the curves collapse on top of each other. There's no dependence on the system size. But when the measurement rate is low, you see that the entanglement depends strongly on the system size. And that suggests that somewhere around here, there's sort of a critical measurement rate that separates a state that's going to volume law entanglement from a state that just has a constant or area law entanglement. Okay, so what we can do if we want to try to estimate where is the critical point and what is the critical exponent, there's no reason that it should be exactly 2D percolation now, and in general it isn't. But what you can do is sort of search for the values of PC and nu that lead to the best scaling collapse. So we write some numerical algorithm that searches for which parameters lead to the smallest dispersion between the curves. And that allows us to, one, scale all these curves on top of each other very nicely, so it looks like there is indeed a critical point with critical scaling around it. And our estimate gives us an estimate for where the critical point is and what the exponent is. In this case, it's about 0.26, which is something non-universal that will depend in general on what class on how you choose your random unitary operators, and a critical exponent that to us looks like about 2. I'll mention that it's actually very hard to get precise numeric estimates of 2, and there's still some uncertainty about what this exponent should be. But what is relatively clear at this point is the following picture for how the entanglement transition works. So there is some critical point, some critical measurement rate that separates what you can call an entangling state, a state where the entanglement continues to grow with time and saturates only finally at something over the system size, from a disentangling state, a state where the entanglement goes to a constant independent of the system size. And this critical point associated with the transition is different from the classical connectivity transition. So there's some classical point that upper bounds where the entanglement transition can happen, at which your quantum circuit literally falls apart into disconnected pieces. And the true transition happens around here. So into this intermediate regime, you should think that there is a connected quantum circuit that nonetheless does not allow entanglement to propagate across the whole system or to grow for an indefinite amount of time.
Brian, there's a question from the audience.
Yes.
Victoria, go ahead.
Well, I have a simple question. The definition for entropy, what you were discussing, the dependence on the size of the system, is still this P log P?
Yes, sorry. So this is something I sort of swept under the rug. In principle, there's a whole family of different measures that they're called the generalized Renyi entropies, that you can have different orders. But what I plotted here was indeed this P log P, or when you have the reduced density matrix, it's the trace of rho log rho. But you think of it as the normal von Neumann entropy.
So 6 means the amount of spins or not? L equal to 6?
Oh, yes. This is the total number of spins in the system. You see it's increasing from 6 up to 24.
Mm-hmm. And you think that formula is still okay?
I mean,
the question is.
Yeah, so I guess you're worried about our numerics being limited to finite system size. And
I was just thinking that maybe when it is like really small amount of spins, the behavior might be a bit different from what you get from the standard like classical statistics. But this is a question. It's not a statement.
Yeah, I mean, the best we can do, I mean, the numerics here are kind of hard because the Hilbert space of the wave function is so very large, 2 to the L. So the best we can do is to go up here and say it looks like the entanglement is growing linearly with size. So in this regime, say that the entanglement after a long time is growing linearly with size, and then we can try to do critical scaling, and well, the data is what it is, I guess.
Okay, thank you.
Anyway, I want to say that, so like Victoria brought up, that the numerics here are hard, and it's really hard to pinpoint exactly where the transition is, what are the critical exponents. I would say that this picture now has a pretty broad consensus. So after a sort of initial flurry on this problem of which we were a part, people have now brought different approaches, different perspectives to this problem, say looking at the entanglement transition from the perspective of mutual information between separate regions, or describing in terms of quantum error correcting codes where an error correction rate is competing with the scrambling rate, or looking at the transition in terms of some effective level statistics. But they all seem to confirm that this picture of a true quantum transition that's below the classical connectivity transition. But it's a sort of a frustrating situation in that we have no exact solution for the critical properties near this quantum transition. So all I was able to give you so far is a description of the sort of classical toy problem, description of the critical properties of the physical connectivity of the circuit, which becomes a description of entanglement only in some sort of special limit. And there's no real handle so far on what this, the critical properties near this transition, or indeed where the transition should be located exactly. All we have is numerics in relatively small sizes. When we got to this situation, there's effectively this 1D classical circuit becomes a problem in two-dimensional statistical mechanics, space and time. And 2D problems are often really difficult to get good solutions for. And so, when you're a condensed matter theorist and you reach such a problem, generally you either say revert to low dimension or you go to infinite dimensions. And what we realize is that maybe this infinite dimensional problem will be more solvable. And what I mean by infinite dimensional is if you have a finite system size and you take the limit of infinite dimensions, that really means that everyone is the nearest neighbor of everyone else. So in a sense, the model that we consider next, you can call it an alt-all model, where every spin is directly coupled to every other one. And you can maybe represent that schematically by this. Sorry, what you're seeing here is arranged around a circle are all the spins in the system. And now your unitary operators can randomly couple any two spins with each other. So that's what these sort of little planks are. The protocols that you select two spins at random, and then you apply a unitary operator between them. And then interspersed with this stack of unitary operators, you occasionally have measurements, which are these sort of red dots, measurements of single spins. So if you were to flatten this circuit out, it might look something like this, where you have your spins evolving in time. And every so often you grab two of them at random, you apply a unitary operator between them, and at a separate rate, you make measurements of single spins. So these measurements now are represented as sort of breaks in the circuit.
Brian, there is another question from Daniel Vargas.
Yes.
Hey, I would like to ask, isn't a better way of thinking of this system as zero-dimensional, as like everything is at the same point and there is no notion of distance?
Yeah, I guess so. I mean, yes, so you're right. So the key point is that there's no concept of spatial separation or spatial distance or spatial regions anymore. So I don't know, in my mind, I guess I think of that it says as everyone being the nearest neighbor of everyone else, but I guess you can call it zero-dimensional if you like. But the point, I guess, is that the system now has, again, only one parameter, and this parameter is the measurement rate R, which I'll basically define as the relative probability of a measurement versus a unitary operator. So the idea is that, at a given point of time, only one of two things can happen next. Either you grab two spins and apply a unitary between them, or you grab one and make a measurement. And the probability of it being a measurement is R, so that if you like, in a given interval of time, there are R times n measurements, and 1 minus R times n unitaries. So a sort of a colorful way of describing this model that's suggested by Golens and Hughes, and I'll come back to this paper later, is you can think of it as a bag of bits. Like you have a bunch of qubits in a bag and you randomly grab two and do some operation between them and throw them back in the bag and shuffle them around again. Okay, at this point, I actually can't resist pointing out a sort of dramatic possible application of this model, which has been suggested recently by Matthew Fisher, is that a model like this might be relevant to thinking about whether there can be quantum entanglement that's relevant for the functioning of your brain. So this is an idea that has really been a passion project of Matthew Fisher recently. And the idea is that in the extracellular fluid of your brain, you have different molecules floating around. And some of these molecules can have a well-protected nuclear spin sitting in a phosphorus atom that has a very long coherence time, 5 minutes or something. And now these molecules floating around in the extracellular fluid can do one of two things. They can either encounter each other, bind together, which is like a unitary operator that couples the two nuclear spins, or they can interact with the synapse. I think the idea is that they fall onto a synapse for a neuron, and then they get endocytosed, they get pulled into the cell, and then once they're in the cell, they can affect the firing rate of the neuron. And that acts like a measurement where some of the nuclear spin now is manifest in the firing rate of the neuron, or the firing of the neuron. So it looks, again, like a bag of these spins that are now undergoing measurement and entanglement with each other and measurement. And then you can ask the question of, can extensive entanglement in the system form, and can it persist for a long time? So, okay, I just mentioned this because it's sort of rare that doing theoretical condensed matter physics has such a dramatic possible application. And I'll also point you to this very nice article by Nicole Younger-Halpern and Elizabeth Crossan that takes this idea so seriously and maps out exactly what the quantum circuit would look like for this problem. Anyway, so the first point I want to make about this problem, if you want to think about how the entanglement behaves, is that you can't think about area law versus volume law. So just like Daniel brought up, there's no concept of spatial regions anymore, so that it doesn't make sense to talk about the entanglement of the left half with the right half. So, maybe another way to put that is that so imagine a very low entangled state where a given spin is, only entangled with one other one. If that other one is as likely to be, if you make an arbitrary partition between left and right, that one other spin with which your spin is entangled is just as likely to be on the right as on the left. So you get sort of volume law entanglement, if you want, for a sort of trivial reason. And that transition, there's no sense in which that transition can diagnose the entanglement. But what you can look at is how information propagates across time. So you can imagine starting with some initial state and then evolving it in time. And this block here, this gray block, is meant to depict some kind of non-unitary time evolution operator, non-unitary, and that involves measurements, renormalization of the wave function each time. And now you can ask the question of, does the final state depend on the initial state? And what I mean is that if I know what goes into the time evolution operator, like I know what unitaries were applied, and I know the outcome of various measurements along the way, is that enough to know the final state? Or do I still need to know the initial state? Is there still mutual information between initial and final state? So the way you can think about this very schematically is that every time you make a measurement, you make a hole in this quantum circuit. You introduce a point where the state of the spin just depends on the outcome of the measurement and not on its past history. And now you can sort of ask the question of, if I sort of grab this circuit and grab the top part, can I just pull it away freely from the bottom part? Or in other words, can you imagine now threading some line, or maybe you should think of it as like a membrane, through the circuit that passes through and separates it into two disconnected pieces. But now the pieces are the sort of top part and the bottom part. So the way that you do this formally is you write down the operator entanglement entropy of the non-unitary time evolution operator. So you have a time evolution operator that takes an initial time state into a final time state, and you calculate the operator entanglement associated with that. So formally, sort of what you're doing is you're imagining your system consists of not n spins, but you're treating it as if it consisted of 2n, and n of those correspond to the initial time, and n correspond to the final time, and you're calculating the entanglement entropy between the initial n and the final n. So that's sort of the idea behind what's happening here. Maybe a clearer way to think about it is, again, a perspective suggested by Gollins and Hughes, where they could say that you could think about this circuit purifying an initial mixed state. So I've been talking everywhere about pure states, but you could also imagine a mixed state that is a statistical ensemble of many different initial states. And then you can ask, if it undergoes this time evolution, does it eventually become a pure state? And in this example, you can see that it would, because these measurements would sort of project all the spins eventually into some particular pure state. Whereas if I'm on the unentangling side, you would have something that was never purified and remained a statistical ensemble forever. Yeah, sorry, there was a question?
Yeah, Anton's got a question.
Yeah, please.
Yep. So I understand that this new definition of how to look at the entanglement in the system is conceptually similar to the other one, but is it really the same? Say, if you apply the same definition to the one-dimensional system, would you get the same critical exponent and the same transition point, or not? So is it now a related concept, or really the same concept?
Yeah, so if you were looking at S naught, if you're looking at the minimal cut, it's certainly the same concept. So I was sort of talking there about making a minimal cut that separates the left half and the right half. But now this is just very slightly redefining it to say, now I want a cut that separates the initial and final time. So I would instead have a cut that's sort of threaded horizontally through the circuit instead of vertically. But it would be controlled by the same critical parameters.
At the cuts, yes, but once again, entanglement is not exactly the same as cuts, and that part is not obvious.
Yeah. I'm not sure the best way to make this more rigorous. Okay, the best I can say for now, and maybe we can come back to this at the end, is that this is the sort of only option that you have available to you to define entanglement transition. Like you don't have an option of defining entanglement in terms of spatial regions. You can only define it in terms of time. And this is the most straightforward definition that extends the concept to talk about entanglement between two times.
All right, that I understand, yes.
Yeah.
Okay, thanks.
Maybe I can try to say something more satisfying at the end, but.
We also have another question from Alila Vasani.
Yeah.
Okay, thanks. I had a quick question. What do you mean by final times? Because if it is like, if you let the circuit run for like infinite times, like with probability 1, you will just measure everything at some step. So it's always like disconnected.
Yeah, actually, I think that's okay, sorry. That is coming very soon. So you're right. So you're right that if I have a finite size system and I evolve it infinitely, then eventually there will always be a point where the initial and final time are disconnected from each other. So really what I should be talking about is in terms of how long does it take before there's no mutual information between the initial and final time? What is the characteristic time scale? And I'll show you that what I call the entangling phase has a time scale that is exponentially long in the system size. So that'll be clearer soon. Sorry, I understand your point. Okay, so as I did last time, let me start with just the classical connectivity problem before I try to approach the full quantum problem. So again, the idea is that I have this circuit that describes different operations. And now let me map it onto a classical graph in an analogous way to what I did in the 1 + 1D problem. So in 1 + 1D, the graph was really simple. It was just a sort of square lattice. But the extension is, again, what I'll do is I'll take each one of these unitary operators and I'll associate with a node in the graph. And I'll draw a link between two nodes if there exists a spin that participates in both unitaries and whose time evolution is unbroken by a measurement in between them. So for example, this orange and this blue, or say this yellow and this purple, both have links between them because there was a spin that is involved in both of them and sort of can transmit information from one event to the other. Whereas on the other hand, say blue and green are not connected because the spin that was involved in both of them gets projected, gets measured along the way. So I, in the end up with a classical graph, and I can talk about the minimal cut that now disconnects the initial time from the final time. So in this case, it would be 2. I cut this and this, or some other pair like this and this, and I will disconnect the initial and the final time from each other. Now, if you want to approach this classical problem, the key idea is to realize that the graph has a sort of a local tree-like structure. What I mean by that is if you take a node somewhere in the middle of the time evolution, somewhere in the middle here, you can arrange all other nodes by their distance from the one you selected. So let me call this purple one that I've selected the root, and I can arrange all other nodes by their distance to the root. So say brown and red and yellow are all distance 1 away, and then, I don't know, orange is distance 2 because you have to go 2 different links to get there, and so on. And what you'll notice is that in the limit where n is very large, this graph locally looks like a tree. It looks like in the sense that you have growing generations of new distinct nodes. And the probability that a given branch of this tree is broken is related to the measurement rate. It comes out to r over 2 minus r, where r again is this measurement rate. So now you can ask the question, well, under which situations can I expect a tree, that there exist trees that grow on infinitely in the limit where the system size and the time are both infinite? And that's a relatively straightforward question. You just ask, okay, to have an infinite tree, or to have an expectation value of the tree size that's grows, what I need is the number of nodes in a given generation to be bigger than the one before it, which basically comes down to a given node should have more children than 1 on average. So that's three links coming out of each node, or potential links. 3 times 1 minus p has to be greater than 1. And from there, you derive the classical connectivity transition that looks like 4/5. Now, you can also derive all the critical exponents associated with the critical point. And I don't really have time. There's actually a very clever argument for where these variables come from. But and if there are questions at the end, I'd be glad to talk about it. But the point is, what you get is that your critical properties depend only on 2 scaling variables. There's t over n to the 1/5, and the delta r, difference in r from the critical measurement rate, times n to the 2/5. This 5 sort of comes from the upper critical dimension for percolation being 6 is 5 plus 1. But again, let me gloss over that for the moment. But what it means is that you should be able to write the minimal cut as a function of only 2 parameters, t over n to the 1/5 and n to the 2/5 times the measurement rate. Okay, so what we can do now is measure exactly the minimal cut density, by which I mean the number of cuts you have to make divided by the system size. And what you see is that it has this sort of critical vanishing as you approach 4/5. And okay, if you plot it on a double log scale, you can convince yourself that the power law of this thing is 5/2. So the minimal cut density grows like measurement rate to the 5/2. Actually, that sort of comes just from the fact that you need this thing to be linearly proportional in n, even in the limit of a very long time. And so you have to raise this parameter to the 5/2, and that's sort of where that comes from. Okay, so now let me mention this issue of timescale, which came up in the last question. Indeed, the way you should think about this is that for a given finite system size, if I allow the time evolution to progress infinitely long, eventually there will be some statistical event that completely disconnects the initial and final time. So the way you should think is that the minimal cut density sort of has some initial transient behavior. Then it has a plateau that you can think of as like the information density, how much information is propagated across time. And it survives for a very long time before it can eventually decays. In particular, it survives for an exponentially long time. That's exponential in the value of the minimal cut. And this is, again, another formula independently suggested by Gollins and Hughes. The way to think about this heuristically, at least in the classical language, is that this minimal cut density is really telling you, if I have the time evolution operator, or I have my circuit, and I want to disconnect initial and final time, then there's some typical number of cuts that I need to make if I sort of wanted to cut through it horizontally at a given time. So a typical cut requires S cuts. And what that means is that the probability of it just happening by chance to require 0 cuts is like e to the minus s. This is like a Poisson statistics. So if a given time slice typically requires s, and so the probability that it would be 0 is e to the minus s, that means that the number of independent time slices you need to look at to find a 0 cut would be e to the s. So that's the rough idea, that the time scale associated with connectivity between the initial and final time grows exponentially with the value of the entanglement, or the value of the minimal cut at least. So here's how that looks in the classical problem. Here's us extracting the time scale associated with exponential decay of s. And what you'll see is that when the measurement rate, if you just look at the inset here, when the measurement rate is above the critical value, that time scale is of order 1. It doesn't depend much on the system size. But when you go below the critical value, then the time scale over which this information persists grows exponentially with the system size and depends very much on the system size, which are these different curves. And in the main figure, you can see that you can do critical scaling and put all this data on top of itself when you plot versus the relevant scaling variables. Okay, so again, this is us sort of solving the classical problem, but what we would really like is to get a handle on the true quantum transition. And now this is pretty much the last point I want to make in this talk. So I sort of showed you before that the key to understanding the classical problem was to realize that it has this local tree structure. So what we decided to do is to look specifically at the entanglement that would come from quantum trees. So now what I'm going to do is I'm going to treat this tree as a quantum circuit, where what I'm doing is I'm sort of taking each unitary of the full quantum circuit, and I'm sort of imagining an incoming node and outgoing nodes, which I can sort of bend around like this to be, you know, upstream and downstream if you want. And now I can ask the question, if I have a single spin at the root of this tree, how much entanglement does it have with all the spins a large number of generations away, which I'll call the leaves? How much entanglement is there between the root and the leaves? And in particular, the question is, if I continue this tree for a very large number of generations, do I still have a finite entanglement between the root and the leaves, or does it go to 0 as the number of generations increases? And how does that depend on the measurement rate? So, you know, in interest of time, I can't really go into the details here, but what we did is to sort of, the entanglement between the root and the leaves is described by a single number. That entanglement, you know, is at most log 2, and it can be anywhere between log 2 and 0. So you can characterize a single number that describes the entanglement, and now you can write a recurrence relation for that number as a function of generations. And so you can ask how it evolves as a function of generations and solve that recurrence relation. And it turns out you can solve it exactly and say exactly where the critical point is on this quantum tree. And it turns out to be this funny expression that works out to be about 0.749. So again, if you draw out what's happening to the entanglement now, and this is real entanglement, not just the minimal cut. If you look at the entanglement in this quantum tree problem, what you get is a situation where you have 2 different points. So you have the transition, and for measurement rate below the transition, you have entanglement that persists indefinitely as you go down to later and later generations of the tree and remains finite. Now, if you go above the classical transition point, then your trees are sort of disconnected from very late generations for a sort of trivial reason, which is that you only have finite trees that die out after just a few generations. And then again, you have this sort of no man's land in between where infinite trees exist, but they do not maintain quantum information for an indefinitely long time, that the entanglement between the root and the very late generations, the leaves, vanishes as exponentially as the number of generations grows. Now you can also sort of figure out in this problem how the entanglement behaves, what its critical behavior is, and it turns out to be exponential in this surprising non-power law form that looks like e to the -1 over delta r. So this is a problem that you can solve exactly, and it's not rely on the classical approximation. And our conjecture is basically that this same critical point should apply to the quantum circuit, basically using the same sort of logic that we used for the classical circuit. And that we also conjecture there should be the same exponential scaling of the entanglement density in the classical circuit, or in the full quantum circuit. So okay, maybe just I can't finish without showing you our efforts to simulate the full quantum circuit. So let me just in the last minute or two show you what happens when you try to simulate exactly this quantum circuit. The important thing I guess you should see is that you can look at the entanglement density and how it decays with time, and you can compare what happens when you're below the critical rate to when you're above the critical rate. So what happens is here when you plot the entanglement as a function of time, it looks like, and again, numerics is very difficult here. It's difficult to get large system size. But it looks like it's going to some finite plateau in the limit of n goes to infinity, that the entanglement density remains finite. Whereas if you're at the transition or above, you see the entanglement transition, you see the entanglement decays to 0 at a time scale that's independent of the system size. Now, the numerics here is sort of hard. Like I mentioned, what we would really like to see is an exponentially long time scale that entanglement persists between the initial and final time over an exponentially long time. And one metric that we thought of to look at is what you call the wave function overlap between two initially orthogonal states. So if you take two states that initially are orthogonal and you ask how much overlap there is between them, then at time 0 they should be orthogonal to each other and the overlap is 0. But if they undergo the same evolution, meaning that they undergo the same series of quantum gates and the same measurement outcomes, same measurements, and here you have to project them onto the exact same measurement outcomes. But if you enforce the same measurement outcomes and have them go through the same unitary operators, you can ask for how long do the two states remain orthogonal. And what you see is that below the transition, they remain orthogonal for a very long time, a time that grows with the system size. Whereas above the transition, they very quickly become the same state. Okay, and now you can try to ask the question of how long is that time scale over which the wave functions remain orthogonal. And what we would expect from our analysis of the tree is that time scale is exponential in n multiplied by something that looks like what the entanglement density is. And so, okay, here's the numerics. The data points represent simulations, and the dashed line is sort of this functional form. And you certainly can't say it's a confirmation of the expectation of our expected functional form, but at least it looks consistent. Okay, so that's pretty much all I have to say. Let me just put up some conclusions here. The main takeaway from this talk is really that in systems where you have both unitary quantum dynamics and measurements, you have a kind of new kind of phase transition. You have a new sort of dynamical protocol, and it's associated with a well-defined measurement rate that separates two distinct dynamical classes. And I showed you how this looks like in 1+1 dimensions. And in the all-to-all case, you have to sort of talk, instead of entanglement between regions, you have to talk about entanglement between initial and final time. And we can solve the classical problem exactly. And it looks like there's a new handle on the quantum transition in terms of these trees. And in particular, we're able to derive exactly where the critical point should be. And we have a suggestion for how the scaling should behave near the critical point. Now, maybe I'll just close by saying that this field is still very ripe for creative ideas, and people are bringing new approaches and new models and new mappings all the time. And there's a lot of room to explore what looks like sort of new universality classes for dynamics. And it's a sort of exciting time to get involved. So, okay, with that, I'll thank you for your kind attention.
All right, thank you, Brian. That was a really great talk. I've definitely learned a lot. Anyone who has questions, please raise your hand and we'll call on you in order. Looks like Lee has the first question.
Thank you for the talk. It was very beautiful and interesting talk. Just two quick questions. Is there any order parameter that can tell between can detect the classical phase transition in this tree, finite tree versus infinite tree? Because you said you had this diagram with quantum phase transition and this classical phase transition for the
yeah, you mean,
yeah, I mean, is there any
this one, for example?
This is this a real phase transition, the classical transition, or is it just that? I mean, real in terms of if I look at the final quantum state or something like that, I can tell whether the circuit is this.
So the classical transition is basically just a percolation transition, and your order parameter could something be like the expectation value for the mass of the tree. And
no, I mean from the the final quantum state. Not, let's say I don't have any information about the circuit, but I only have the final quantum state. Is there any difference between two sides of this classical transition?
That's a good question. So I guess there is a sense in which something on the right side fills a smaller portion of the Hilbert space, and something on the left fills all the Hilbert space, but in some portions it only has exponentially small contributions there. So if you were to ask a question like how how much information do I need to exactly represent the quantum state, then this classical transition would represent, I think, a transition in how expensive it is to exactly write down the quantum state.
But isn't that the entropy basically?
Well, so that is essentially the S0 entropy. So S0 is exactly that quantity. But something like the von Neumann entropy takes into account, like if two things are extremely weakly entangled, it counts the strength of the entanglement in the entropy. Whereas if you need to write it down exactly in such a way that you have to write down all those extremely small numbers, then you care. Like there's a very sharp difference between literally zero entanglement and a tiny amount. That's maybe the most heuristic thing I can say.
Okay, another quick question. Is there any reason that you didn't look at the Clifford circuit? Because like this geometric thing seems like just geometric. So it shouldn't really matter if you put like Clifford unitaries or like R random unitaries. But then with Clifford, you can go to like much larger systems. So.
Yeah, that's right. So actually there's been a lot of work, people doing Clifford circuits, and we didn't do it ourselves, but there are a lot of papers of people diagnosing this transition, especially in 1+1D. Using Clifford circuits.
Yeah, I was wondering why was there like a special reason that Clifford doesn't work, or you just didn't?
Well, Clifford circuits, they are somehow less entangling, by which I mean that your unitary operators are drawn from an extremely restricted part of the Hilbert space, and they somehow mediate less entanglement. So the belief at the moment, I think, is that the transition that you see in the Clifford circuits does not represent the same thing you would get from generic random unitaries. So I think there's a discussion still about whether they belong to the same universality class or not.
Okay.
So we for the moment at least, we're trying to avoid making that assumption unless we have to. But I agree, you pay for it in terms of numerics being much harder.
Okay, thank you.
Thank you.
We have a question from Braden Ware.
Hi, yeah. So I was wondering whether you considered at all doing partial measurements in place of, and tuning the sort of tuning from no measurement to a full measurement, say by and sort of the upside is that you can get rid of the disorder that comes from choosing the measurement locations. So you can measure everywhere, but partially instead of at random locations, but with complete measurements. And I was wondering whether you think that dramatically changes the results.
Right. So I know that in 1+1D, that's a problem that Matthew Fisher was working on. You probably know that too. And the conclusion there seems to be that even when the measurements are distributed uniformly in space, there is a transition as a function of the measurement strength. We haven't thought, or at least I haven't thought about what the analog of that result is in the all-to-all circuit yet. So I don't have anything really smart to tell you, unfortunately.
Okay, thanks.
Daniel, go ahead.
Thank you. Yeah, I would like to go back to my previous question about whether this is zero or infinite dimensional, because these structures look more infinite dimensional in the end.
Yeah.
I kind of lost track of the argument how you arrive at having this tree and no loops. And I guess I kind of missed what is the process exactly that's happening here. Like, is it 1 2 qubit unitary per time step? Or does the number of unitaries scale up with the system size?
Right. Okay. Yes. Sorry. So let's. Okay. Let me just. So the protocol exactly is that you have n spins, or n qubits, and at any given time point, there are two different things you can do. You can either grab two at random and apply a unitary between them, or you can grab one at random and measure its Z component. So what we call R is just the relative rate of the second thing happening versus the first. But that's the whole model. So I guess whether you want to call that zero dimensional, infinite dimensional, I don't know that there's anything more deep than naming there. But I think of it as infinite dimensional really because everyone is directly coupled to everyone else, which is what you would have like, in the same sense that we talk about like the Sherrington-Kirkpatrick model or something being an infinite dimensional limit of a spin glass.
And so how do you end up with the trees?
Okay, right.
That's that.
Right, right. Okay, so there is something that I probably should have said more clearly, is that the tree structure really relies on n being very large. So the idea is that like I started a given node. Okay, so if you understand the mapping between the circuit and the classical graph, the idea is that you start at a given node and then map out all other nodes in terms of their distance from the original one. And you get a tree with no loops if the probability of, you know, following, basically if there's only one path between any two nodes. Now, if, like you're saying, that if n is finite, you always have a finite probability of there being loops, where say there are two different ways to get to this orange one. And then what you have is not strictly a tree anymore. But in the limit where n goes very, very large, the probability of there being two such paths falls. In other words, the typical size of loops becomes log n. So up to a log n number of generations, you can describe your system as a tree.
Thank you.
Yeah.
I believe Anton had the next question, actually.
Yep. Let me see. Oh yes. So I understand that the transition to the unentangled phase cannot happen below the classical percolation transition. Mm-hmm. That's just because the system falls into different parts.
Right.
But I'm wondering if also we know that the critical point for transition into the disentangling phase is not universal. So I'm wondering if there's any sense of optimality, say how close can you make the distance between, how close can you bring the point of disentangling transition to the classical percolation threshold? Maybe there's some simple unitary evolution that guarantees that as long as the system doesn't fall apart, it's still entangled.
Yeah, that's a good question. You know, in a sense, applying these so we chose, let me go back. When we studied this problem, we chose for our unitary operators what you call hard random unitaries, meaning the unitary operators selected at random from the space of all possible unitary operators. Sorry, I don't know why I'm going back to this picture. Each unitary is, and you expect that to somehow be maximally entangling. And even then there's a pretty big separation. So the one handle that we have, I think, on making the quantum transition approach the classical one is to take the value of the spin as not 1/2, but some large value. And as you make the local Hilbert space associated with each spin bigger and bigger and bigger, then the quantum transition will approach the classical one.
Yeah. But how is our distribution maximally entangling if it literally contains gates that do nothing at all?
Yeah, I mean, I guess the idea is that the probability density of such gates that do nothing is vanishingly small, and that much more likely it is to have things that are very close to maximally entangling somehow.
But is that even right? I mean, HAR includes all gates, and these are all 2-qubit gates, so we're dealing with a small Hilbert space, and a fair fraction of it doesn't do much of what you want.
Yeah, I mean that's true. I mean, I don't know. Adam and Jonathan can probably make a deeper comment on this, but I mean, the alternative, it seems to me, would be to have a gate that depends on the state of the things that it's acting on, which is a very different model. So I don't know a more clever answer to your question, unfortunately.
All right.
All right, I think Babak was next.
Yep. Thanks for a great talk. I think I have 1.5 questions. So the half is, so I understand all the measurements that you have here are uncorrelated, right?
Yeah.
You don't have any correlation between the measurement.
Okay. Yeah. So sorry. This is a point. For most of this talk, I should probably be clear about this. For most of this talk, each of these measurements is just chosen by the Born rule. So I mean, you take the wave function at that time, and you say the probability of up or down. You pick one of them according to the relevant probabilities, and you project onto that.
Okay.
For the tree case specifically, we did not do that and had a predefined projection that we used. Otherwise, it's very hard to write a recurrence relation. You have to sort of pre-choose what the projection will be. We just took them all to be up. So in that sense, there's a very subtle difference for that case. And I probably should have said that more carefully.
Okay, so that's a fixed projection, but the various projections are still basically uncorrelated.
Yeah, I mean, they're all just, in the tree case, they're all just chosen to be up.
Right, I see, okay.
Yeah.
Now, I think the question I'm wondering is, how would your results change if there is correlation, and specifically I'm thinking of maybe having the same measuring device basically measure, which means if I wanted to include it, I would basically entangle the system with the measuring device. Mm-hmm. And so you have this loss of entanglement in the system, and perhaps the entanglement with the device is increasing or something like that.
I don't think I have anything very intelligent to say, aside from the fact that there are people thinking along those directions, that a measurement is really a interaction with some big ancilla qubit or something like that. And unfortunately, I can't summarize off the top of my head, but I can say there are people thinking in that direction. And offline, I can maybe point you to the relevant papers.
Sure, thank you.
There's also a question from Max McGinley. Max, I think you can unmute yourself.
Hi, yeah. Just quickly, so you say there's a difference in the critical transition.
Sorry, I'm trying to find the relevant video for the person who's talking, and it's surprisingly difficult.
Oh, sorry.
Okay, all right, I see you now. Okay, please continue.
Yeah, so there's a difference in the critical point depending on whether you're looking at this minimal cut versus the actual von Neumann, and I guess those both come under generalized Renyi entropies. So
that's right. Yeah.
What happens to sort of say second, third Renyi entropy, etc.?
Yeah. Right. So there's a nice mathematical identity here that I didn't include, that basically says that the difference between that all Renyi entropies above n equals 1 are all have to be within a constant of each other. Like there's some bounding factor that's like n over n minus 1 or something. And they all have to be within n over n minus 1 of S infinity. So the idea is that all the Renyi entropies above 1 should behave equivalently. So we're sort of, and they all correspond to sort of the same generic universality class. So S equals 1, I guess you're sitting right at the boundary, but we generally take the von Neumann entropy to be, or any of the higher ones, S2, to be sort of all representative of the same universal behavior. Sorry, I don't have that written down on the slides, but I can pull it up and send it to you if you're curious.
I guess there's some work that says that when you have a conservation law without measurements, there's some difference between von Neumann and Renyi entropies in terms of diffusion versus ballistic spreading. Do you think there's any? I guess it's just it would be a guess, but do you think there's any signature of that when you include measurements as well?
Now, the first thing I should say is that we haven't looked at any kind of conservation law, so maybe there's something different there. But in everything that we've done so far, that's just random unitaries and measurements, there seems to be no difference between the Renyis and any of the higher, between the von Neumann entropy and any of the higher Renyi entropies.
Okay, makes sense. Thanks.
Sure.
There are no more questions from the audience, but I have a couple real quick. Now this, Anton was talking to you also a little bit about this disentangled but not quite classical thing.
Yeah.
In between, and I remember back in the days when I took a quantum information theory course, that there's this concept of quantum discord, and I was wondering, which is where the density matrix has non-classical correlations, which is not entanglement. Is that related at all here?
Sorry, I have to say I never took a quantum information class, so this is probably a vocabulary word that I haven't learned, and I'm sorry about that.
Sure. Okay, we can chat offline about that. And then separately, one thing that's kind of nice about this is, if I'm thinking from an experimentalist perspective, where we're trying to create stable quantum systems, which are subject to all these random measurements, which are decays and the things that we don't like. So you're showing this nice behavior as a function of random entangling gates, but I wonder if we then said, okay, can this start to give us some insights on how we can design these entangling gates to make a stable extended state with a lot of entanglement?
Right. That is a deceptively difficult problem, because the transition that I'm talking about is basically a transition where you make measurements and you write down the outcome of each measurement. And this is a different question than, I have a system that's undergoing decoherence to the environment, where basically there was some kind of measurement, but I don't know its outcome. Asking the question of how do you experimentally probe this transition is a kind of tricky one, and so far the only answers are kind of brute force ones, where you have to, prepare the system many times and look at the make a sequence of measurements many times. So the question of I guess the short answer is that there's a distinction between those two things, between making measurements and writing down the outcome, and having a system that's interacting with the environment and undergoing decoherence somehow. And I personally don't have any really wise words about how to bridge the gap there. Although again, that's something that Adam and Jonathan at Stitity might be able to comment on.
Actually, Anton just asked a nice question in the chat. Is like, is randomness in the gate? Oh, in the gate choice, excuse me. Okay, maybe a relevant question is, if the gates are not so random but ordered, but your measurements are random, does that change anything?
Yeah, actually, so we explicitly checked this in the 1+1D case, that we had the same unitary operator we applied over and over and over again. And the only measurement was in the location and the outcome of the only randomness was in the location of location and outcome of the measurements. And the answer is that everything behaves the same, except that the location of the critical point, the critical measurement rate, can drift depending on how entangling your gate is, what you chose for your gate. But to say that the scaling, the existence of the transition, the critical exponent all seems to be the same. And actually, this question of which randomness is really critical is one that's still being acted on. Like, maybe even the location of measurements isn't critical, but even just the outcome of measurements, randomness of outcome, could be enough to give you some transition. So it's kind of unclear which randomness is really essential to the transition.
So how far to the right does the transition tend to drift if you choose a non-random? Yeah, that one.
Yeah, so, okay, I think the current estimates are, so when we took a non-random unitary, it drifted from like 0.26 down to 0.22.
Huh.
If you do the Clifford circuit, which is somehow less random, it drifts all the way down to 0.15.
So it only becomes worse.
Yeah, it's hard. Yeah, they keep drifting to the left. It's very hard to find something that drifts to the right, except by increasing the spin value Q.
Okay, and it looks like there are no further questions. So thanks again, Brian, for the great talk and all your patience with our questions.
Thank you, guys. It was a lot of fun.
Great, and we'll look forward to having you all here again in 2 weeks. Thanks again.
All right. Thank you. Thank you.
Thank you.